The first part of this week, we generalized the notion of a function of a single variable to a function of an array. We need this for very many different settings, both to solve classical differential equations such as Navier-Stokes and quantum such as Schrödinger or Heisenberg quantum mechanics. Today, we go back. We go from an array of variables back to single variable. It's magic. We'll be able to study very large matrices or even infinite dimensional operators and evaluate them as though they were just single numbers. The magic that does this is called eigenvectors and eigenfunctions, German word for self or proper. Eigenvalues and eigenfunctions. Take a D by D matrix. Look at the determinant of that matrix minus variable lambda times identity and solve the characteristic equation. Now, this is D by D matrix, so now when I expand it by any method I know, you'll have all powers of lambda from D to 0, and I can always factor the polynomial. It's just basic thing about polynomials. If matrix is real, roots are either real or complex pairs. This matrix acts on d-dimensional vectors. And once you have found your eigenvalues by any means, like in love and war, here everything is allowed. Run your Mathematical, whatever, you'll get an array of numbers. They'll be real or complex. So list them as lambda 1, lambda 2, lambda d. To make life simple, use a rule that the real part of lambda I is larger than the real part or equal with the degenerate. To the next one. If a matrix is just a random, some matrix pull our head, this probability 1, all the eigenvalues will be different. These are the eigenvalues. Now, what are the eigenvectors? An eigenvector is a very special vector which has a property that when you apply the matrix to it, so a vector is a direction in linear space. So there are directions in which when you apply the matrix, you just get the scalar number back along the matrix. So while in the general direction, matrix moves the vector and chases all components, for eigenvectors, the only thing it does is it returns a number. That number could be something very simple, like 1 or minus 1, meaning the matrix is symmetric or antisymmetric, stuff like that. But these numbers can be very meaningful. And you can easily show that if lambda I not equals lambda j, then EI and eigenvector j, they have to be linearly independent. So these are eigenvalues and eigenfunctions. It's simplest to start by considering the most general case. So let's assume eigenvalues are all distinct. We have the linearly independent eigenvectors. And as they're linearly independent, there are d of them, we can use them as a basis for any d-dimensional vector. So if you take The d-dimensional vector is, let's say, real components. They could be also complex. Then I can use this basis to write it as a sum of eigenvectors, presumably normalized, each one normalized to 1, if we are doing this, and they span the space. The combination of a matrix minus identity times any eigenvalue. So what that means is that this combination annihilates eigenvector I, because this difference is 0. If I take a product of all of them, when I apply it on the sum of it, this product, we have terms which annihilate every single vector in this sum. So acting on arbitrary vector x, this always returns 0. It's a humble fact, and it has some important names attached to it. What Hamilton-Cayley theorem says is that the matrix satisfies its own characteristic equation. So this object is a matrix. It has d square components, and this combination magically sets all of them equal to 0. Let's look at this product and just delete one term from the product. Because we have deleted one of the terms, this thing is not equal to 0. So what does this thing do? Well, apply to x sum of x1, our eigenbasis. What this product does is apply to every one of these guys. This returns 0 unless we apply to the ith one, for example, the first one, that it doesn't give 0. Now, acting on the surviving eigendirection, it gives me and then just picks out ith eigendirection. So to make this a little bit nicer, you can get rid of this prefactor lambda I lambda j by dividing by it. So you define the product of all these terms divided by lambda I minus lambda j over all directions in a space other than ith direction. And this is called projection operator. Really what it does is applied on any vector in this space, it returns the value of this vector along ith component. It's called projection operator. You know, you have space in d dimensions. You can go in any dimension. To pull out the subspace, which is along eigendirection, so in this case it's one-dimensional. In general, it's some finite number of dimensions, smaller than dimension of the whole space. This projection operator just pulls that out. And to use it, only thing you need to know is eigenvalues and the matrix itself. So this is very simple to use and evaluate in the practice. And we have it since 1850s, Euler, Lagrange, Sylvester. This projection operator has some nice properties, the way it's written. So these are matrices, Liberty matrices. If you multiply two of them, if they're the same, this normalization factor guarantees that the first one pulls the direction out, the eigenvector, and the second one doesn't do anything more because there's no extra prefactor. So they have a property that squared, they're idempotent, they just return themselves without any factor. And they're mutually orthogonal. So there is a Kronecker delta and no sum on J's. Not only that, but one of them pulls one eigendirection, the next one pulls the other direction, the third one pulls the next one. And if you sum all of them, in this case, we're assuming they're all distinct, so there are B of them. If there are fewer distinct eigenvalues, then it's the number of distinct eigenvalues. But some of them is simply the identity matrix. Because what that sum does, it takes this vector and pulls out its components along all the directions, each one of them. And when you add them all up, as in the sum, you just get the vector back, nothing has changed. So we have orthogonality. They're not just orthonormal, meaning that if they're different, the angle is 90 degrees, they're zero. But they're also orthogonal because their square is 1, so that act like unit eigenvector correlates. And you have completeness. If this number distinct eigenvalues less than D, then two things can happen. One is that this discussion I give you just decomposes the big space not into directions, one-dimensional directions, but subspace as a given dimension. That's called full reducibility of a space, irreducible representation, irreps, etc. Take home is there is a thing called projection operator. And it's very easy to remember. It just says, take a matrix, subtract on diagonal any of its eigenvalue, take a product of all possible things except one. Normalize it just by replacing matrix downstairs with its eigenvalue on the subspace. And that reduces working with a large matrix to just working with one number on the subspace. In other words, we're reversing what we did in the first set of lectures. Whenever you have a function, you can generalize it as a function of big arrays. Whenever you have a function of operators, you can simplify your calculation by splitting it into little pieces. In each piece, in each irreducible representation, your operator goes from a huge matrix just to one number. The main take-home of this week is that if problems can be formulated as linear problems, then you can manipulate large arrays of information data about quantum state or about numbers of stocks and investments using notions, classical notions of one-dimensional functions such as exponential and logarithms. That was lesson number 1. Lesson number 2. When I do calculations with these large arrays, I can use the eigenvalues and eigenfunctions of matrices that I'm working with to construct an intrinsic coordinate frame in which the calculation is one-dimensional. Very complicated and we collapse.